Yeah, so I think we can get started. My name is Wanda, and today we will talk about I will talk about the deep learning on Yarn, running TensorFlow and other frameworks um, on the Hadoop cluster. So a little bit about myself and my colleague. So I'm Wanda Tan, and I'm Apache Hadoop PMC member, and mostly focused on the GPU and deep learning for now. And previously, I worked a lot of scheduler features, such as load label, preemption, etc. So my colleague Sunil, he cannot join this time because of the visa issue. So he is also a Apache Hadoop PMC member, and he also working on the similar field, scheduler and deep learning related stuffs. Okay. So this is agenda today. So today I will talk about the machine learning basics, just to set up some context, and machine learning in production, and how Yarn can help to run a machine learning workload. And the last is some examples about running distributed TensorFlow and some other stuffs on Yarn. Okay, so for the machine learning basics, so let's assume we are trying to build a cat classifier, which we will give a picture and try to predict it is a cat or not cat. So first, you need a lot of data. You need to label data. So which means you already know that this data is for cat or non-cat, and this is tagged to the picture. Okay, and this will be fed to the algorithms. For example, fed to deep learning models or any other machine learning models. This training data will feed to the model, and the model will run in the training in recursively running the training for a long time. And once this is done, it will save the models to a storage for the future use. And when this model is get saved, we can use this model to do the predict. So that means if you have any picture which the model never see before, you can use this model to give to the, you can use the picture give to the model, and the model can give you what's the probability of this picture belongs to cat or not cat. And about the model training, so there are a couple of steps of the model training. One is the first one is training, and also we need to do model evaluation. So evaluation means once the training is done or during the training in process, we give the model some samples which the model never see before, and ask the model to predict to see how the model works. So this is also a way to get the ideas about how the model will work after finish. And the model validation means once the training is done and once the model is saved, we can try to give some real data to the model to see how the model works. And once everything is done, we will stage the model. We'll put to a stage, and for the future, we can use this model. So there are two categories of the model training, or the in general machine learning models. So one is we call it traditional machine learning models. So that means these models are invented a long time ago. They are not as shiny as deep learning models, but they are still very useful. And in many fields, it is not replaceable by the deep learning models. So they are logistic regressions, gradient boost trees, recommendation AOS, and LDA. So there are many other kind of models like this. Typically, we will use the Apache, MLDeep, or XGBoost, and many others like Lib, SVM, etc. to do this model training. And the other category is we will talk more about is the deep learning models, such as DNN, CNN, NN, and LSTM. We will use the popular libraries like TensorFlow, MXNet, and PyTorch, etc. to do the training, and Caffe, of course. The next thing is why we need GPU to do the training. So because GPU has many tiny cores to handle massive but much simpler computation tasks simultaneously. So let's look at the example. The CPU has less cores, but each core is very powerful. It can handle very complex logics, like any control flows, things like that. And for the GPU, it's different. The GPU has many cores, but each core is very simple. So for the task like matrix computation, etc., the GPU can handle them very well. And because GPU, the design of the chip is to doing this kind of tasks. So let's assume we have a machine learning task. For example, here is a neural network, is a Google Net. So we can for this kind of machine learning task, we can divide the computation to two parts. One is GPU computation intensive, which is simpler matrix operations, and the others is very simple tasks. Very simple in computation, but complex. For example, the control flow. So when the deep learning framework gets started, it will looking for its local GPUs and map the computation intensive part to GPU and others to the CPU. And when it is doing training, the time spent on GPU becomes very less because the GPU is good at handling this task. So the overall, so this one is off. Excuse me. So this monitor is off. Yeah, so this monitor is off. Could you help me to check? Yeah, so let me continue. So the reason we're doing GPU, when we use GPU is without GPU support, researchers and engineers almost impossible to wait for the job to finish because many training jobs will take several weeks to finish, and we cannot waiting for so long to get the feedback of any parameter changes. So I'm going to talk about, thank you. So I'm going to talk about machine learning in production. If you go to some website, for example, Tensorflow, you can find the machine learning in tutorial. It's so simple. You can use the command to launch the Docker command to launch the Docker container, and inside that you can do in all the trainings and follow the tutorials to do the trainings like that. However, this is oversimplified. So in production, the actual case is like this. So the machine learning is the core of machine learning is only the tiny piece in the middle. It is complex, but compared to our system, it's only a small part. We need to have the configuration to, for example, some system to store the configuration and some system to handle the data collection. And we need to do the feature stretching. So, for example, we can use the Spark, so which I will talk about later, to do the feature stretching. And we need to do the data verification, machine resource management. So this part is Yarn will do this. And also the process management tools, Yarn and OS and Docker container, for example, will handle this. And serving infrastructure. So this means once the model is saved, we need to serving this as a service. So basically, you can post some REST request to the serving service and get the result. Also, we need monitoring to see what's the training going on and what's the state of the cluster. Also, the training is not always simple. A single model. We may need a pipeline to do this. So let's assume we are building a machine learning program for the predict how the customer will think a restaurant's food. So basically we can take two parts. One is text and one is is pictures. So for the text, the customer may comment saying that burger is great. However, the onion ring overcooked. We can build a word embedding model to understand what's the emotion of the customer. Is it feels good or feels bad? And also we can use the pictures taken by the customer to build a food picture classifier model to say if the food looks delicious or food looks bad. And we can, given the two models, we can build another in-symbol model to combine the two and give the result. And we need to build the data pipelines for the machine learning under the big data context. So let's assume we may have some sensors on the edge to take pictures or get any other data. We can use Li-Fi and other tools to get this data into the data lake. And also the data lake may have some other data, for example, the user log, like that. And the data scientist can use Apache Zeppelin or Jupyter to do the data exploration, to print some histograms and some other things to understand this data. Now, once the data scientist has some basic understanding of the data, they can define the ETL pipelines. For example, they need to use Hive or Spark to do the join sampling and feature stretching, and we need to split the training and test data for the later training. And once all this is done, this will goes to the deep learning model to do the training, and deep learning frameworks to do the training. So how Yarn can help here? So for Yarn, we are very focused on two things. One is data. All the applications or services running on Yarn, they are more or less interact with data. And also we are care about sharing. We want the first is applications running on Yarn can share the infrastructure which is provided by Yarn. Another thing is we want the applications can share resource in the same cluster. So let's assume we have some hardwares, CPU, GPU, and SSDs, and we have some storage systems. And on top of this, we can have Yarn. And on Yarn, we can run in the batch jobs or interactive queries like Hive, LLAP, and Spark. Also, we can run in some machine learning workload like Spark, MLlib, XGBoost, and TensorFlow. And the data scientist can use Zeppelin or Jupyter to use all the underlying software to do the machine learning job. So why we put everything under Yarn? So as a normal cluster user, they care about many things. For example, they care about SLA. They don't want the things to be late. And they want to better monitoring their cluster and training job. And they care about quotas. They don't want one user to take all the resource from other users. And they care about isolation. They don't want process share the same node, interact with each other, so affect each other's running. Excuse me. So as a Yarn user, we have these following solutions. For SLA, we have capacity planning. So which means we can plan the capacities for each queue users, etc. So everybody can get its own share to finish their job. And we have preemption to make sure if somebody takes more resources than it's granted, the Yarn will take back the resource from the overused users or queues. And we have reservation systems you can reserve the resource upfront. For the monitoring, we have timeline services inside Yarn and some other ecosystem projects like Grafana. We can build some very nice graphs to let the user or admin to understand what is happening. For the quotas, we can assign quotas to queues and users, And also we can enforce user access control to, for some resource, we only give the resource to some of the user to use. For example, if we have some GPUs in the cluster, we can say only some of the department can use this resource. About isolation, we currently have CPU, memory, and GPU FPGA isolation. And for the rest of the isolations, it's work in progress. So let's see an example about how all this workload running on the same Yarn platform. So let's assume we have 5 nodes. Each node has 128 gigabytes. So we are using Yarn to manage this cluster. And we are running, we can run test jobs on some of the node, running Spark on some of the node, and we can run AOLAP on the other node to do the as a long-running service to do the SQL queries. Yeah, so we can have some new budget to buy some GPUs to the cluster. We add some GPU node, and we can add this node to Yarn to let the Yarn to manage this node. And on top of that, we can run in Tensorflow, Caffe, and MXNet to consume the GPU resource. So there are some recent works in Yarn to support machine learning workload, such as Tensorflow. So there are GPU isolation and scheduling support, and native service. So which means we can very easy to define and run any custom services. So I will talk both the two later. So the two features are available in Apache Hadoop 3.1, which we released 2 weeks ago. It's April 6th. Yeah, so for the GPU support on Yarn, first question is why we need isolation. This is because multiple processes can if we put multiple processes to use the single GPU, so what happens is the second one trying to use the GPU resource needs to wait for the first one finish. So this will cause the second one starved or the work get delayed. Also, for some frameworks like TensorFlow, they will try to catch the GPU memory very aggressively. So that means if we place 2 TensorFlow applications or process on a single GPU card, both of them cannot run. They will out of memory. So that's why we need this. For the GPU isolation on Yarn, the granularity is per GPU device. So that means we are not going to support allocate half GPU to process. This is because CUDA or NVIDIA don't have such functionalities to do the partial GPU isolation. And so once the process is assigned on GPU, we'll use C groups and Docker to enforce the isolation. So the enforce means the process cannot go and try to do the jailbreak to get the GPUs from the other applications. And for the Docker plus GPU support, this is also very important. This is because many machine learning platforms has dependencies like Python, R, or CUDN, or CUDA. So, and because these libraries are all involving, that means we cannot let the user to install these libraries on the physical machine or virtual machine, which will be shared by everybody. So the better approach is to use Docker to isolate these packages and inside the application. And so the Docker is good, but the problem is it can introduce some other problems. The problem is if the GPU base library inside the Docker container is conflict to the host OS and GPU base library, which including drivers, etc. If the conflict happens, we cannot run the Docker container. So solution of this is to use the NVIDIA Docker plugin to which will detect the the host OS based GPU based library, including the driver, and the NVIDIA Docker plugin will automatically mount this volume to the Docker when it is launched. So and when we try to build the Docker image, we will not put the GPU-based library. We will use the host OS GPU library. So that is the solution. And for Yarn 3.1, we support Docker and also the NVIDIA Docker plugin. So I'm going to talk about running distributed TensorFlow on Yarn. So first question is why we want to run distributed TensorFlow. So the reason is if we use more GPU to train a model, for many of the model or framework, they can scale very, very well when we add in more resource. So the y-axis is throughput. So if we put so here is 64 GPUs and here is 32 GPUs. So basically the libraries like NVIDIA and or PyTorch or MXNet, they can scale very well. And how distributed TensorFlow works? So here's a very kind of simplified distributed TensorFlow architecture. So on the left side, it is some workers. The workers will try to use the data and running matrix computations and to calculate what the value of the parameters should be. And on the right side is parameter servers. So once the worker gets the parameters updated, it will send the new updated parameters to the parameter server. So the parameter server will hold in all these parameters. Typically, they will not use GPU. So basically, you can think it's a shared memory cache for all the workers. And to make it work, TensorFlow provides one solution is to construct a tf-config environment. And what inside that should be, first is a cluster spec, which will mention all the endpoint of parameter servers and workers. And also for each task, the one who launched the job needs to specify the task index and type. So once the task gets launched, it can say, hey, I am index 1's worker, and this is my peer's endpoint. So the task knows which one to contact. Yeah, but so one thing to mention that even we have the environment variable can be set. This is still a very bad overhead to the users to use distributed TensorFlow because you have to SSH to each node, set this environment, and to launch the job. So this is not a very pleasant thing to do. So what we're trying to simplify is which is a job name and also the path to the spec. An example of the so later I will talk more about what the spec should be. And under the hood, what happened is the spec will submit to Yarn Resource Manager, and Resource Manager will launch the application master parameter servers. And once this is launched, according to the pre-specified environment, they can find its peers to work. So you don't have to understand all of this. So Yarn will handle this automatically for the users. So I'm talking about how to write a service spec to run distributed TensorFlow. So basically, we need to define what's the name of the service. and what's the Docker image of each task. And also we can define a list of components. Here is worker and parameter server. And if we expand this, you can see that this is a spec for the definitions for the worker component. So basically, we can have the launch command specified, and how many resources we needed. Here we can specify the GPU. So once Yarn will see this, and the Yarn knows which node to allocate and how to do the isolation. The user don't need to worry about this. And specify how many workers of this task, and specify the TF config. Also, this is an example about how to serve already trained TensorFlow model. So similarly, we define the name, the artifact name, and also the number of containers. So in the future, we will support Yarn will automatically balance the request to the launched workers. And also, so this example uses a simple TensorFlow serving. This is a data project. Comparing to the original TensorFlow serving project, this is very simple one to use. And also, once the service is get launched, it will Yarn will generate the DNS entry for this service. It will be serving job and domain name port. And so the other applications can use this endpoint to access the model. So actually, this so when you look at this, this may still seems a bit complicated. So you still need to write a spec, even if it's much better than manually do this. So we are working on a wrapper to simplify this. So I'm going to do a demo for this wrapper. Oh yeah, so there's another example is to write the service spec to run MXNet. So this model, this spec consists two parts. One is prepare. Prepare is doing some download the data and prepare the what needs to be trained. And also the fine tune is a training process by using the downloaded data. And also in the second module, the fine tune module, we can specify the dependency to be prepared. So when Yarn sees this, Yarn knows the first one is to be started and finished first, then launch the second one. So we can orchestration the workflows here inside the service spec as well. Yeah, so regarding to the XGBoost applications running on GPU and Spark, so Yanbo will have a talk. I think it's the next room in the so after my talk and after this session. So yeah, so if you have interest, you can go to check Yanbo and Minje's talk. Yeah, so I'm going to do the demo. Yeah, sorry. So somehow the mouse cannot move to the right. So let me unplug this. Yeah, so this is a pre-recorded video. So we're creating this wrapper. We currently temporarily call it DL wrapper, but we may think some better name for this. And we will specify the name of the training job and specify the Docker image. We will specify the number of workers and do we need TensorBoard or not. And we will specify how many GPUs we want. So Yarn will figure out the isolation. And we will specify the job dir, so which means where the training checkpoint will stored. We specify HDFS folder here. And for the water launch command, we currently this use census data, so it's a famous data set, and we will specify the LD library path to access the CUDA libraries, and Java Home and Hadoop HDFS Home to access the HDFS inside the Docker container. And we're going to copy this and go to the command line to run this job. So this is started and submit to your, let me have the point. Yeah, so you can see that and this is currently in accepted state. And so accepted means the yarn is received this request and starting to allocate the resource. And now it's in started state, means service is started. And now if you look at this, this print out the TensorBoard link. And once you click the link, it goes to the web page, the TensorBoard of this job. So you can view the training process on this page, and you can get to understand how the training goes on. Yeah, so this is this work is still in process, and we hope to finish this and maybe for the next summit we hope to do a better demo. Yeah, so that is all the talk I have. So any questions? So could you so if you have question, maybe you can use this microphone.
So thank you very much for this talk. I had a question which I actually posed to your colleague before lunch.
Yeah.
It's about doing deep learning with basically Spark, or in this case you don't use Spark, just directly Yarn. So deep learning is by nature an iterative process. When you try to chunk it out, I'm still not quite clear how you can make benefit of the parallelism. Because you need to know what is the latest state of weights, and then you use your newest batch to first do the inference and then see your errors and then correct the weights. So maybe it would be great if you could elaborate on that point. I think that figure which you showed with the trainers and the parameter server is related to this question.
Okay,
Thanks.
so my question is how. Just to clarify, so your question is about how Yarn can make the trainers and parameter servers can work well. Is that your?
My question is more specifically about, it is not about Yarn itself, but about doing deep learning in this distributed fashion. So where do you gain exactly, given that it is actually an iterative algorithm?
Okay, gotcha, understand. So basically, and of course, if you run in workload in distributed, that means the workload will spend more time on the network communication, right? So that's and that is overhead we have. So what's the so actually this is not related to Yarn. So for the deep learning frameworks, what it do is so it will for each waters they will train based on its own data, and training for a little while, and it will update the parameters to the parameter server. So they try to not do the update very frequent. They try to less frequently do the update the parameter. And maybe I'm not quite sure about what's the time because this is varies, but they try to minimize the network overhead.
If you have 3 batches
Mm-hmm.
and training in parallel,
Mm-hmm.
then the first one will come up with some first set of updated parameters. The second one will come up with a completely different set of updated parameters.
Mm-hmm.
So, because like I said, because it is actually in nature an iterative algorithm, and in this case, if you do it in parallel, what do you do? Who updates the parameter?
Oh yeah, so basically the update parameter is you can think it's an aggregated value. So everybody will tell the parameter server this is my updated value, and depends on the algorithm. The parameter will aggregate these values. For example, it may do some average of these parameters like that.
So is this what TensorFlow does?
Yeah.
Is this something you implement?
No. So this is not what I implemented. This is TensorFlow and all the other framework do. For example, the MXNet doing the similar thing. The parameter server is a general concept. Yeah. Yeah, no problem. So any other questions? Okay. So if so if you have any questions, we can chat offline. Thank you.